Hi. So today I wanted to go over a general overview of machine learning and kind of try to break it down to a 5-year-old level as to how exactly machine learning works. So starting off, the very first concept that we have to understand is the concept of a neural network. And neural networks are very straightforward. Essentially, with a neural network, what we're trying to do is mimic what the human brain does. That's the best equation that we have to understand this problem right now. And so offhand and up front, when you first start talking about this, the complexity starts here because there's a fundamental problem with this equation from jump, which is that we do not 100% understand how this works. What we know about this, the human brain, is that it's made up of neurons, and so neurons fire in the brain, and in the human brain there's billions and billions and trillions of neurons that are firing off, and they fire off, and then that is what produces thought and action and everything behind that. So what a neural network tries to do is attempt to mimic this, and the flaw in the equation there is that so while we do know that there is a correlation between number of neurons and how this works, what we also know is that there isn't a direct correlation, and we don't know anything about that missing gap. So putting that into real-world terms, there are animals that are in existence that have more neurons than the human brain does, but we've pretty conclusively shown that those animals are not smarter than people. Their brain is not smarter in any traditional sense. So number of neurons doesn't necessarily equate to the full potential power of the brain, and we don't know what that missing element is. So when we talk about everything here forward, we can only talk about essentially what we know about the brain in this equation, which is that it operates off of neurons, and those neurons fire, and that's what creates action. So when we build out a neural network, we're going off of essentially that assumption. We want to mimic how this works. And then so how we mimic how this works is through hardware. And then so each individual node could be an individual server, a computer, a piece of hardware that can process and compute. And individual node could be one individual piece of hardware, or one node could be comprised of multiple servers. You could have maybe a huge node that you want to have and make it the most complex equation possible, and it's going to crunch huge numbers. So then maybe that node is comprised of 6 servers itself, and then all of this is just all of these make up one node. Or it could be each one of these is an individual node. And then the other thing to keep in mind with this is that it's, again, just something that can process or compute. So you could take a full row of 1,000 Pentium 1 133 megahertz computers and create a neural network out of that. And that would be your neural network. It wouldn't function very well. It wouldn't be, its performance would be lacking in a lot of areas. But it would be a neural network. And then so at a base level, that's what we're talking about, is nodes. And then so essentially, again, going back to this human brain analogy, a node, again, is equivalent to a neuron. But to understand the full elements of a neural network, essentially, what you start off with is, again, your node, so your physical hardware, and then you have data sources that are feeding into this neural network. That data source is the key piece of this, all of the data that you're directly feeding into the node. And then from there, essentially, you have your hardware, and then you have your framework, and then also your model. I like to refer to the model also as methodology. And then so if you're familiar with different disciplines, framework and methodology, that's exactly what this is. And it's following out and mapping this out. So all of this is very recently was something that didn't exist. So people, not myself, not anyone, created these concepts and created the concept of what is AI, going back to the 1960s and Alan Turing when essentially kind of like the birth of AI, if you will. these discussions had to be had. How exactly do you set this up? And so the academic frameworks that are used across multiple disciplines, like framework and methodology, all of those principles and a lot of those principles are prevalent throughout this, because what other way is there to set up a model like this? So just recapping where we're at so far, a neural network is made up of nodes, and nodes are kind of the equivalent of neurons within the brain. And then the full elements that you need to make up a neural network are a piece of hardware, the data sets that you're feeding it so it can learn on, the framework that it's going to use to learn on, and then the model that you're going to use, like how it's going to learn. And we'll dive deeper into these concepts. So first of all, diving into the framework concept and going over what a framework dictates. And I apologize for my mouse being a bit skippy here. So with framework, essentially a framework just it dictates what programming languages can be used, what algorithms can be used, and it also dictates the model that can be used. So frameworks, there's essentially three big frameworks that are in existence right now. The first big one is owned by Google. The second one is backed by Facebook, and then there's a third one that's backed by and licensed, that's open sourced. And those are kind of that's Python based, and those are the three framework models that you can choose that are out on the market right now. And then so when you talk about framework is the overarching structure of the brain. Framework dictates what this brain is going to look like and how exactly this brain can function. Like, what are the base level limitations and functionality, and what all can this brain do? If you packed it full of neurons and you made this the most powerful brain in the world, it's still the number of neurons is still directly correlated and needs to also be fed and restricted by the framework. And then, so once you understand the framework, then the next level that you go down to is the model. And the model that you use is essentially the rules that the machine is going to use while it learns. So, and there are various models in existence. And then when you talk about AI, so to me, there's two complex parts of this equation at a base level. The first complex part is the brain, like the fact that we don't understand what the brain is and how the brain works. But the second most complex part of this equation is the model itself. And so here is where all of the complexity for this comes in. This is where you need like the PhD background, all of this. How exactly should you structure this, and what exact model should you be using and utilizing for the exact situation? This is the huge complex part. So just understand at a base level that at a core level there's three kind of like broad models that are used, and then so if you don't have a PhD background, these are the models that you would utilize to support and build on. It's unsupervised, supervised, and reinforced. Unsupervised is just generally you feed in data and you kind of just let the machine do its thing. Like here's all of the data, learn on the data. You can do what you want. Supervised is here's all of the data and start learning on the data, but we want you to learn and specifically focus on learning X. And like drive towards a kind of like a specific goal. Whereas reinforcement is like positive and negative reinforcement. And like so if you if like for example you're creating a video game and you don't want the AI to fall off of a cliff, if there's a cliff there, you would give the AI negative reinforcement anytime that it falls off of a cliff. But you also, in that same instance, want to make sure that the AI explores, so you give it positive reinforcement for exploring its environment, but negative reinforcement the second that it starts to get towards or close to that cliff. And so that's kind of how that model works. And these are the kind of the three broad models. If you don't have the PhD background, you just really have to understand at a base level how the models work, and you can go from there. And that's kind of honestly where I am at. as far as my level. When I don't have a PhD in computer engineering, so I don't like, this is my level of complexity here. But going down here, then essentially you work down into the next layer, which is essentially like the question or the questions that you want the neural network to solve for will always dictate the complexity of the model required. So essentially what this means is that you have to plan out all of this from jump. When you create a neural network, you have to start at the very base level and map it all out. You can't ever go into a machine learning project as an agile type project. It wouldn't work. You literally cannot use agile project methodology within machine learning. You have to map out, here is our end goal, here's the result, and all of it has to be mapped end to end when you go into it. And then so when you do that end to end mapping up front, the very first step that you take after you do that end to end mapping is, okay, what is the least amount of complexity that we need in order to solve that problem? When you're building out a neural network, you have to look at all of the costs associated with it. Of course, in a dream world, you would want to build out a neural network that's the size of the sun. But in a more feasible terms, if you are just asking a simple problem, such as asking it to recognize images, for example, then you don't need a neural network that's the size of the sun to do that. You need a much more simplistic brain that could be able to handle that equation. And so the size of the brain that you want is dictated based off of all of these requirements up front. And so when we're talking about the size of the brain and into that equation, that brings us down to the next layer here, which is essentially the very first thing that you want to ask within that size of the brain is, how simple or complex is the question that I'm asking at a fundamental level? And then so what this is illustrating here is, let's say, for example, the question that I have is, I want an AI to be able to identify cats versus dogs in images. And then so I'll give it an image of a cat, and then it will tell me if it's a cat or a dog. And then same thing with a dog. I'll give it a picture of a dog, and it'll tell me if it's a cat or a dog. That is a very simple question to ask. And that, like, asking a question like that is nowhere near the same as asking a question as what we're looking at here on the right, which would be which house is worth more if we were to sell the house on the right or the house on the left. For a human, that's a very simple equation to solve. I can just look at this picture and the house on the left, obviously. But an AI can't do that. So you need to feed a machine can't do that. You need to feed it the data that it can utilize in order to make this equation. And then it has to learn everything about that equation from jump. So an equation such as which one of these houses would sell for more money to an AI is a very, very complex question, because you have to give it every single element that could be possibly associated with this problem in order for it to solve the answer. So you have to give it data sets on historical pricing of houses, historical pricing via region, via like square footage of the house, features of the house, over time, like any variable that you would want to utilize in your model has to be fed into this. So it becomes a very complex model. And then so that's kind of the difference there in explaining simple versus complex networks, and the kind of that very first step that you want to take when you're building out your neural network. So the next concept to understand then is, so we have our neural network built out, we have modeled it out, we want to build it, we have our question established, and then we know whether or not we want to build a simple or a complex network. Then essentially, let's put all of that together. And then so when we put all of this together, so the hardware, the data that we're feeding into it, the questions that we want to ask, the framework that we're going to build the brain on, essentially the shape of the brain, and then the logic that we're going to give the brain, like the rules that we're going to put behind it. When you combine all of that together, essentially what you get is, to me, like the equivalent of a little baby. So you have your neural network. Like it is, at this point, you have a complete neural network, and it is capable of answering the question that you want to ask. And then, so for simplicity's sake, let's say that this little baby here is representative of a neural network that wants to answer the question of cats versus dogs. And so that's what this little baby is. And so essentially, when we build out all of this and we build out our model, when we build out the framework for it, and we say, okay, these are the rules that you're going to use to identify what exactly is a cat or a dog. This is the data sources that you're going to use to learn on, etc. All of that together equals the little baby. And then, so kind of sticking on this baby analogy, when going back to the complexity of the neural network and the question that we're asking, all of that, you can think of that kind of like, again, in terms of baby, the complexity of the neural network that you build out determines what kind of baby that you get. Like, are you going to get a baby ant, or is it going to be a baby dog, or a baby dolphin, or like equating it out to kind of like the best available AIs on the market right now. Like ChatGPT would be like a human baby. And then, on down to ant level would be maybe like a homebrew AI, that like a machine learning algorithm that someone has like spun up, and they have their database that they're feeding into it, and it's a little ant doing work for them. So the other thing to keep in mind with that equation as well is that again, it's the power of the neural network is what makes up like what kind of baby that you're going to get, and like that size of the brain of the baby, and then so every single element that is incorporated, that's a part of the neural network, all of them combined is what equals like the brain size, equals what kind of baby that you're going to get. So, for example, I could have like I could take the Pentium 1 133 megahertz, but then I could utilize the PyTorch, which would be like the most kind of like the newest framework that's on them available right now. And then I got a room full of blue ribbon PhDs, and they came up with a revolutionary model, and then I gave it access to all of the data in the world. We're still going to get like at most like maybe like a little baby kitten, or maybe like a little baby bird, because it's not like because this element is still missing from the equation. And then if we had all of the elements needed there, then we could get maybe like a super baby. If we only want to answer a very basic question, again, we can just set all of this up in a really simple way. Just use off-the-shelf and open source software for a lot of this, and then so make it really cheap. We just have a really simple question that we want to use. We have a lot of internal first-party data that we have. We just need a little ant in order to take care of that. And then so again, it's a human baby isn't always the best in all situations. Like you don't always need a human baby. Sometimes you just need an ant, or sometimes you need a bird. And then so it's just what exactly do you need is for it to answer that question is what's going to dictate what is the best neural network in your exact situation. And so the last thing that I want to kind of illustrate with this concept is that essentially when you combine all of this, so when you look at a neural network on its own, like we have built out our neural network, we've given it the data sources, the framework, the methodology, it's become a baby, we chose what baby it is, and then we started training it. And then so we train it up and we train it up. and then it grows up from a baby, and then it turns into a person, or a bird, or a dog, or an ant. And then, so if we take essentially like this equation, that would be person number one. What we can't do is afterwards, like after we have completed the training of this person, we've created the baby and we trained it to become a baby, and then we trained it from a baby into a person. We can't go back and then say, hey, become like a different, like start as a different type of baby, but become like a girl version of The Rock. Like, it wouldn't be able to do that. If we wanted to do that, we would have to create a whole brand new person from scratch. And then so every single time that you have a new model like that you have to introduce within this, or like you have to retrain the algorithm on like different data sets, or most of this is when you have to update or make changes to the model, then that's where you get like the new person, and it would always be a new person. And then like the best simple way to explain that out would be if you think about ChatGPT, and then so all of the versions that are out right now, like ChatGPT 3, ChatGPT 4, ChatGPT 2, and then so those like ChatGPT 2, ChatGPT 3, they're still in existence. You can still utilize them, and they still do certain things. And also the other thing to keep in mind is that it's not always a 100% enhancement. Person number one is going to have different traits than person number two, and somewhat like different strengths and weaknesses. So while ChatGPT 3 might be like the superior model across the board and overall, there could be things that ChatGPT 2 is just way better at ChatGPT 3 than, and like in that area, because of all of these individual elements combined made person 2 different than person 1, and person 2 just became really strong in that area where person 2 didn't, or where person 1 didn't. And then so you have to weigh in those types of things when building out a neural network. So overall, just summation, I understand it's a very complex subject, and it's hard to wrap your brain around. And I think the reason why it's hard to wrap your brain around is just going back to this, the fact that we don't know exactly how the brain works. So all of this is a fundamentally flawed in several ways, possibly, equation from jump, because we don't know what we don't know about this. So all of this and everything that stems from this is just based off of our base assumptions of this, which is that if you want to make this bigger, add more of these. If you want to make this more powerful, make these more powerful. And so that's